Back now, we're going to do our first example on the expansion of materials. In our first example, the question says there's a brass ball with diameter 2.54 centimeters and a brass ring with inner diameter 2.55 centimeters. Assume the initial temperature is 24.1. How much should the brass ball be heated up so as to not fit inside the ring? So we're assuming we are only heating up the brass ball, but the ring is staying at 24.1 Celsius, right? The alpha of the brass is 19 times 10 to the minus 6, so we're going to be using this equation, okay? So how will we proceed? We have V final is equal to V initial plus delta V, and then delta V is equal to 3 alpha V initial delta T, right? Remember we proved in the theory section that delta V is 3 alpha V initial, and then we can factor out the V initial, right? And then V final is going to be 4/3 pi times the final radius cubed, 4/3 pi times the initial radius cubed, 1 plus 3 alpha delta T, right? And then the 4/3 pi cancel. Okay, in the problem, the diameter of the ball was given, but it really doesn't matter because the radius final is equal to the diameter final over 2. So we can put that in there, so we don't really have to calculate the radius per se. And then the 8 and the 8 cancel, and then so we can just work with the diameter, right? So if we want the brass ball to barely fit inside of the ring, we want it to have the same diameter, right? So the final diameter should be 2.55 cubed. The initial diameter is 2.54 cubed. 1 plus 3, and then the alpha is going to be 19 times 10 to the minus 6 times delta T. And then what are we solving for here? The delta T, right? 2.54 cubed. And then we're going to just solve for delta T, right? So we can get our calculator. We can say 2.55 divided by 2.54 to the power 3. And then subtract 1 from there, minus 1. Right? And then divided by... Right, so that's how much the temperature should be increased of the brass ball in order for it to not be able to fit into the ring, right? So then, if its initial temperature was equal to 24.1, we add that to this, and then the final temperature comes out to be equal to 232.1 Celsius, okay? Now, what if we were heating both of them? Would it be possible, would they ever reach the same diameter? Because the ring is actually starting out bigger. What if we heated both of them simultaneously? Let's see if we get a solution. The brass ball is going to increase its diameter, and the ring is going to increase its diameter. So is the brass ball ever going to catch up to the ring? So let's see this. Okay, so now let's come up for an equation for just the final diameter of the ball. The final of the ball is going to be equal to the initial of the ball times cube root of 1 plus 3 alpha delta T, right? And then let's come up with an equation for the diameter of the ring. Well, since the ring looks like this, right? The ring looks like this, and then the ball looks like this, right? So the ball is increasing its volume as a volume, but the ring is increasing its inner diameter, just like the length expansion equation, right? The outer diameter is going to increase, but we don't really care about the outer diameter increase. Then the inner diameter is going to increase, right? And therefore the opening of the ring is also going to get larger, but which one is going to get larger quicker, right? So for the inner diameter of the ring, we can just use the linear expansion equation, right? So we have the final of the ring into here, right? And then what's the initial of the ring? The 2.55. So let's just put the equation in right now. Right? And then now we can put here 2.54 cube root of 1 plus 3 times 19 times 10 to the minus 6 times delta T is equal to 2.55 1 plus 19 times 10 to the minus 6 delta T. So one is expanding linearly, and then one is expanding like a cube root, right? And let's see if they can catch up. Okay, so now let's cool them down, and cool them down actually to below absolute zero. So that means this is not doable. Well, what happened? What happened was that the ball's diameter increases like a cubic function, right? So it started out at 2.54 and it starts increasing cubically, right? And then this is temperature. And then the ring's diameter increases linearly like this. So this is 2.55, this is the ring, this is the ball, and they never cross. Unless, of course, they were different materials. Let's assume that the ball was lead and the ring was still brass, right? So the ball was lead, and the alpha of lead is 29 times 10 to the minus 6. Then it's a possibility that they're gonna cross, right? Because lead has 29 coefficient of expansion, and then the brass has 19. So the only thing that we're gonna change then is put here 29, right, into our equation. Now this is doable because since it is a larger number than that, a cubic function might actually be able to meet with the ring and then go like this, and he might actually cross it twice. So let's put this 29 into solver and let's see what I get. Of course, this is a lot, something like 22,000 Celsius, right? So we don't need to do that. So if all I need to do is increase the temperature by 410 Celsius. So if I add the initial temperature to that, 24.1, that's gonna be 434.78 Celsius. And then that's my final answer. So that gives me the first answer that I was looking for. So if they were different materials and if the ball was expanding quicker, then it would be possible for the ball size to be the same size as the ring, even though both of them were being heated simultaneously, okay? Thank you very much.